Dear children, hearty welcome to today's class. Last class, we were discussing about the different factors which affect vapor pressure. Today, we are discussing one of the another properties of liquids, that is refraction and optical exaltation. Here, we will discussing about refraction and refractive index, specific refraction, molar refraction, and finally we will discuss about optical exaltation. First, we will see what is refraction. Refraction is the bending of light when light travels from one medium to another. That is, we will see the definition. Refraction is the bending of light when light travels from one medium to another. That is, we will see this by drawing one diagram. Here we have our liquid and here we have our air. Okay. When light travels in air, the direction of light will be like this, and when light travels in liquid, it shows some variation or it bends. That means the light ray is refracted. We can say that the light ray is refracted. This is nothing but refraction. Refraction is the bending of light when light travels from one medium to another. The medium. So, here when the light travels from one medium to another, the medium where the light is incident is called it as incident medium. Here the air is the incident medium. Here air is the incident medium, and where the light is refracted, that is called refracted medium. Here the liquid is the refracted medium. The refraction is caused by two factors. First one is the change in direction and the second one is speed of light. First one is change in direction and second one is speed of light. If you look into here, in the incident medium, that is in air, the direction of light is 1, and when it is in liquid, the direction changes. That is what? The change in direction. The second one is speed of light. That is, the light is having one speed in air and another speed in liquid. Because of this difference in the speed of light, the refraction occurs. Therefore, the factors which affect refraction are change in direction and the speed of light. We know that the light travels in different speeds in different medium. It travels in air in one speed or it travels in vacuum in one speed. It travels in liquid, different liquids in different speed. And according to the wavelength also the properties changed. Then when the light travels here, the angle where here incident, that is called it as angle of incidence, and here the angle where the light is refracted is called it as angle of refraction, that is called it as R. So one is an incident angle and the another one is refracted angle. Therefore, the refractive index, if we take refractive index, that is N, that is defined as the ratio of the sine of I and R. Refractive index is defined as the ratio of the sine of I and R. Refractive index n is equal to sine I by sine R. The refractive index n is equal to sine I by sine R. Okay, now we have seen the definition of refraction and what is incident medium, what is refracted medium, and what is the cause of refraction and what is refractive index. Now, we can see that what is the reason behind the refraction. That is, the light is having different speeds in different medium. That is the reason for the refraction. When the light travels in vacuum, it is having high speed. What will happen when light travels in liquid? The liquid is having some polarization and therefore the liquid is, some electric field is generating in liquids, and the electric field which is generating in the liquid is opposed by the electric field in the light. That is why the speed of the light is reducing in the case of liquids. Okay, I hope you understood the reason behind the slow or the reduction of speed in the case of liquid compared to the air. Once again I say, in the light is having different speeds in different medium. When light travels in vacuum, it is having high speed. When light travels in liquid, the liquid is having some polarization of atoms. Because of this polarization, some electric field is generating, and this electric field is opposed by the electric field of the light. Therefore, what happens? The speed of the light is decreasing in liquid. That is the reason behind the refraction. The value of n, that is refractive index, also depends upon the light we used. If we use the sodium line, D line of sodium, the refractive index will be different, and if we use another X-ray wavelength, X-ray, then the refractive index will be different. If we use different lights, then the refractive index of the liquid also will be different. The light travels slow in air than vacuum. The velocity of light, that is V, the velocity of light V is equal to c by n. The velocity of light V is equal to c by n. Here V is the velocity of light in a medium and c is the velocity of light in vacuum and n is the refractive index. V is the velocity of light in medium, c is the velocity of light in vacuum and n is the refractive index of the medium. If we want to calculate the refractive index, that is n, here we have our equation V is equal to c by n. Now our job is to find out the refractive index, that is n, that is nothing but c by V. That is, c is the velocity of light in vacuum, that is c, then the divided by the velocity of light in the liquid. Here we come into the definition of refractive index. The refractive index of a liquid is defined as the ratio of the velocity of light in vacuum to the velocity of light in the liquid. Refractive index of a liquid is defined as the ratio of the velocity of light in vacuum to the velocity of light in the liquid. that is n is equal to velocity of light in vacuum c divided by velocity of light in the liquid v. Here both are velocity, therefore refractive index has no dimensions. Both will get cancelled, then the refractive index has no dimensions. This refractive index n value will change according to the temperature. The n value will change according to the temperature. The reason is that as the temperature increases, the kinetic energy of the molecules in the liquid also increases. As the kinetic energy of the molecules increases, what will happen? The space between the liquids also, the space between the molecules in the liquids also increases. Then the oleum will be increasing. Oleum will be increasing means the density will be decreasing. The density of the liquids will be decreasing. When the density decreases, what will happen? The refractive index also increases with the increase in temperature. So, when the density decreases, what will happen? The velocity of light, this causes the refractive index to increase. Okay, once again I repeat the refractive, how the temperature affect the refractive index. That is, as the temperature of a liquid increases, the molecules move faster and the oleum increases due to a decrease in the intermolecular attraction, so its density decreases. This causes an increase in the velocity of light in the liquid. As a result, the refractive index of a liquid increases with increase in temperature. Here, if we see here, the molecules are like this in a vessel. Molecules are arranged like this in the case of liquids. And as the temperature increases, the molecules can move faster. As the molecules move faster, what will happen? The oleum increases. The oleum increases. As the oleum increases, what will happen? If the oleum is increasing like this, now beginning the oleum was here we have only here we had the molecules. Then once the temperature increases, the molecules move faster and the oleum increases. Here we got the oleum. That means in this oleum only this much molecules are there, only this much molecules there. Then what will happen? The density decreases. Density is nothing but mass by unit oleum. In the unit oleum, the number of molecules are decreasing, therefore density also decreases. Once the density decreases, what will happen? The velocity of light also increases. Velocity of the light also increases. Therefore, the refractive index of a liquid increases with increase in temperature. I hope you understood how the temperature affects the refractive index. The refractive index of a liquid also affect the wavelength of the light we used. If we use high wavelength of light, then the refractive index will be lowering. Here if we have taken water and benzene, here at 434 nanometer, the water is having the refractive index of 1.34, and at 589 nanometer it is 1.33. At 656 nanometer it is 1.331. That means as we see here, the refractive index of water in 434 nanometer, 589 nanometer and 656 nanometer, the refractive index is low at 656 nanometer. That is, At high wavelength of light, the refractive index is decreasing. In the case of benzene also same. At 434 nanometer, the refractive index N is 1.524. At 589 nanometer, it is 1.501. At 656 nanometer, benzene's refractive index is 1.492. The refractive index is increasing as the wavelength of light increases. Here we come to an end of refraction and refractive index. I hope you understood what is refraction and refractive index and what are the things which affect the refraction and refractive index. What is the reason for the refraction? Now, let us see another property, that is specific refraction. That is specific refraction. This specific refraction is a relation that connects to the density of a liquid and refractive index. That is something connected to the N and rho. N is the refractive index and rho is the density of a liquid. N is refractive index and rho is the density of a liquid. This specific refraction can be denoted by Rs. R is capital letter and S is the suffix. This Rs is specific refraction. The equation to find out the specific refraction is n square minus 1 divided by n square plus 2 into 1 by rho. I repeat, Rs is equal to n square minus 1 divided by n square plus 2 into 1 by rho, where n is the refractive index and rho is the density of the liquid. Rs is the specific refraction. This specific refraction equation, also known as Lorentz equation, because this equation is found out by two scientists, L. V. Lorentz and H. A. Lorentz. Next question is, when we change the temperature, whether the specific refraction will increase or not? That is the question. Here, when we increase the temperature, the variation of the N is compensated by the variation of density. Therefore, the Rs value, that is the specific refraction, remains constant. If we explain this little more, here when we increase temperature, what will happen? The n square value will increase, refractive index value will increase. So, here this n value and this n value, that will be higher. Then this n value, the increase in the n value is compensated by the density of the liquid. Therefore, the specific refraction value remains constant when we increase temperature. This is about specific refraction. The equation is Rs is equal to n square minus 1 divided by n square plus 2 into 1 by rho. This equation is also known as Lorentz equation, and the temperature is independent for specific refraction. Next, we are going to see another property of liquid, that is molar refraction. That is molar refraction. The molar refraction is the product of the specific refraction and molecular mass of the liquid. Molar refraction, Rm of a liquid, is defined as the product of its specific refraction, that is Rs, and its molecular mass. when we express this in equation, Rm is equal to Rs into M. We know that what is Rs. Rs is nothing but specific refraction. The equation is n square minus 1 divided by n square plus 2 into 1 by rho. So, Rm, that is molar refraction, is n square minus 1 divided by n square plus 2 into m by rho. This is molar refraction equation. That is here Rm, that is molar refraction, is equal to n square minus 1 divided by n square plus 2 into m by rho, where n is refractive index, m is molecular mass, and rho is the density. Then Rm, here also R is capital letter and m is suffix. Here we have m by rho. This m by rho we can replace by Vm, that is nothing but molar oleum. Then the equation becomes Rm is equal to n square minus 1 divided by n square plus 2 into Vm. This is the equation when we replace n by rho with the molar oleum. If we use infinite wavelength of light, that means the wavelength of light is very high, that time the n will be very large. When the n will be large, that will be approximately equal, so that Rm attains the limiting value of m by rho. So, if we have a high wavelength of light, that time high wavelength of light means the refractive index also will be large. Then that time what will happen? This Rm will be approximately equal to the Vm, that is nothing but the molar oleum. Molar oleum will be limiting. That means the n also will be large, and this n will be large when we use large wavelength of light. When n is large, this Rm will attain the maximum value of m by rho, that is molar oleum. Limiting value of m by rho, that is molar oleum. This molar refraction is having a structural importance. That means this property is both additive and structural. Therefore, this molar refraction property of the liquid is useful for the structural elucidation of compounds. If you do not know any compound, then if we are isolating that compound from the mixture, but especially in the case of alkaloids or terpenoids, then if we want to get some molecules, some compounds, this molar refraction value is very helpful for the structural elucidation of compounds. Here we have a table for the molar refraction value of some elements. Here carbon is 2.591, hydrogen is 1.028, oxygen minus OH hydroxy group 1.518, and oxygen in carbonyl group, that is 2.573. Using this table, now we can do one problem. Our job is to find out the molar refraction of acetic acid. We are writing acetic acid, that is CH3C double bond OH. Okay. We have two carbons. Therefore, for carbon 2 into, in the table we have carbon value, molar refraction value, that is 2.591. Then we have 4 hydrogens, that is hydrogen 4 into 1.028. Then we have 2 types of oxygen. One is oxygen in OH. That is OH oxygen value is 1.518. That is 1 into 1.518. Oxygen in CO, the value is 2.573. All these are in, all values are in centimeter cube per mole, centimeter cube per mole. All these values are in centimeter cube per mole. Here we have 4 hydrogens, okay, correct. Then we have 2 carbons, correct. Then we have 1 OH, okay, correct. Then we have 1 COO, that is correct. Then if we multiply this, when we multiply this, he will get one answer. Here also we will multiply, one answer will get. Here the same 1.518, here also 2.573. When we add all these things, the final answer will be 13.85 centimeter cube mole inverse. This is the answer we will get, that is the calculated value for molar refraction of acetic acid, and the observed value is 13.3 centimeter cube mole inverse. This is about molar refraction. Now, let us see another property of liquid, that is optical exaltation. Optical exaltation, that is the another property of liquid. This property occurs when we calculate the molar refraction of using some molar refraction values. When we calculated the value of some of the compounds, what happened? Some molecules are having the conjugation, especially the conjugated molecules. 2 or more double bonds. Conjugated means 2 or more double bonds. There, the molar refraction value showed some high value for the observed value. Observed value was higher than the calculated value. Observed value was higher, the calculated value was less. That discrepancy was found in the case of the compounds which showed 2 or more double bonds or conjugated molecules. That phenomenon is called it as optical exaltation. So, the optical exaltation property comes when the compounds are having 2 or more double bonds. That time what will happen? The observed value will be higher than that of the calculated value of the molar refraction. Here we have some examples. If we take 2,4-hexadiene, 2,4-hexadiene means in the second position and the fourth position we have double bonds. This is first carbon, second carbon, third carbon, fourth carbon and fifth carbon. Here we have sixth carbon. So, in the second position we have double bond, and in the fourth position also we have double bond. Here it is CH3. Here we have one hydrogen. 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 Here we have 3 hydrogens. Okay. This is 2,4-hexadiene. 2,4 carbon valencies are correct, I think. Okay, it is correct. Then when they found out the molar refraction value of 2,4-hexadiene, what happened means the observed molar value was 1.76 units higher than the calculated value. 1.76 units higher than calculated value. That means it shows some optical exaltation. That phenomenon is called it as optical exaltation. The molar refraction value showed some higher value. The observed value was higher than that of the calculated value. Second is 1,5-hexadiene. 1,5-hexadiene, that is this is first carbon, second carbon, third carbon, fifth carbon, sixth carbon. And in the first position we have double bond, and in the fifth position we have double bond. Then here CH3, here one hydrogen, here we have one hydrogen, here we have two hydrogens, here we have CH, one hydrogen, here we have one hydrogen. Okay, this is 1,5-hexadiene. In the case of 1,5-hexadiene, it is not conjugated molecule. There, the observed value was 0.12 less than calculated value. In the case of 1,5-hexadiene, the observed value Rm was 0.12 less than calculated value. But when we look into the 1,3,5-hexatriene, there also conjugation is there. There the value was, the molar refraction value was higher. The observed value was higher than the calculated value. The observed value was 30.58 centimeter cube mole inverse, but the calculated value was 22.28 centimeter cube mole inverse. The observed molar refraction value was higher than that of the calculated molar refraction value in the case of 1,3,5-hexatriene also. The case of 1,3,5-hexatriene also there is conjugation. The double bonds are there in the first position, second position and fifth position. Conjugation means alternate double bonds are there. Hexatriene means, hexa means 6 carbons. So 6 carbons are there. Then triene means it is 3 double bonds are there in alternate positions. That is 1,3,5-hexatriene. So when we look into this 2,4-hexadiene, 1,5-hexadiene and 1,3,5-hexatriene, when the molecule shows some conjugation, in that cases the observed value was higher than that of the calculated value. That is, these molecules showed some optical exaltation. But the molecule here 1,5-hexadiene is there. There the observed value was less than the calculated value. Structural elucidation of compounds. Molar refraction, we already said that the molar refraction help for the structural elucidation of compounds. Here, if we know the molar refraction and the optical exaltation value, we can distinguish the alpha and beta isomeric terpenes, and ketoenol tautomerism of ethyl acetoacetate. That is the structural elucidation application of molar refraction and optical exaltation. I am not going to deal with the how we can distinguish this alpha and beta isomeric terpenes and ketoenol tautomerism of ethyl acetoacetate. Just this statement, the optical exaltation and molar refraction property will help to identify the isomeric properties of alpha and beta terpenes, or we can identify whether it is alpha terpene or beta terpene, and ketoenol tautomerism of ethyl acetoacetate. So this is about optical exaltation. Here in this module we discussed about refraction, refractive index, specific refraction, molar refraction, and finally we discussed optical exaltation. With this we wind up this session. Thank you.